Let's talk about cosets. So given a group G and H a subgroup of G, can define for each G in G H times G. As this notation suggests, this is the product H times G as H runs over all the elements of H. This is called a right coset of H. And you can similarly define G times H to be GH, where H belongs to H. This is called a left coset of H. So basically you've taken this subgroup H and then you've multiplied all its elements on the right by an element G of G. Let's look at an example of this thing, a very natural example that comes up in number theory. Take G to be Z, the group of integers under addition, and take H to be the subgroup of, say, multiples of 5. Then if I want to write, so let's take any element of G, let's take the element 3. So I want to write the coset H times 3, but since the group structure here is given by addition, I'll write H plus 3. And this is equal to H plus 3, where H belongs to 5Z. This is also the same as 5K plus 3, where K is in Z. So this is just the set of all integers which leave a remainder 3 when divided by 5. And this is also the same as 3 plus H, because in this group of integers under addition, A plus B is B plus A. So addition is commutative. So whether I write 3 plus H here or H plus 3, it's all the same. This is what's called an abelian group. Okay, let's look at a slightly more interesting example. Okay, so let's take G to be the group Sn, the symmetric group on n letters, and let's take H to be the subgroup of those permutations in Sn which take n to n. All the permutations in Sn which take 1 to n to n. Now these permutations, they will also take, since they take n to n, any number strictly less than n must go to another number strictly less than n, because n is already taken. So this group can be thought of as also permutations of the numbers 1 to n minus 1. So this is isomorphic to Sn minus 1. So this is a way of thinking of Sn minus 1 as a subgroup of Sn. And now let's ask ourselves, what are the cosets of H in G? So here's a nice observation. So suppose I take some element W0 in Sn. Okay, so take some element. And let's look at W0H. So this is equal to, by definition, W0U, where U of n is equal to n. Okay, so I ask, where does W0U take n itself? W0U takes n to, it takes it to, U takes n to n, so it takes it to W0n. So I claim that W0H is the set of all W in Sn such that W of n is equal to W0 of n. And we've already seen one way that each element of W0H has this property. And to see the converse, we just need to say that suppose W of n is equal to W0 of n. Okay, then we ask, is W of the form W0 times U, where U takes n to n? And so we just have to find this element U, and if you think about it a bit, you'll probably come up with the same answer as me, which is that you take U to be, So let's just do some rough work here. I want W0U to be W. So I want U to be W0 inverse times W. Okay, so take U to be W0 inverse times W. Then what is U of n? U of n is W0 inverse W of n, but we know that W of n is W0 of n. But that's just n. So that shows that the coset W0H is just the set of all elements of Sn which take n to W0n. So the upshot of this is that H, which is isomorphic to Sn minus 1, has n left cosets in Sn. They are given by Cn is equal to W in Sn such that W of n is equal to, no, not Cn, I want to say Ci, where W of n is equal to I for I equals 1 to n. And what we have is Sn is a disjoint union of I goes from 1 to n of Ci. Okay, so what we are going to be interested in now is how a group decomposes into cosets. So firstly, what is the size of a coset? Okay, so what is the cardinality of H times G? So G is some group, little g is an element of G, and H is a subgroup. I claim that this is the same as the cardinality of H because you have a bijection from H to, I'll call it Rg, right multiplication by G, from H to Hg. This is the function which takes H to H times G, is a bijection. Why is this a bijection? Well, it's a bijection because its inverse is given by right multiplication by just G inverse, x goes to x G inverse. You can check that. So if you have an element in Hg, you multiply it by G inverse, you'll end up with an element in H. So each coset has the same cardinality as the group itself, as the subgroup itself. Okay. Now a good way to understand these cosets is to use what we already learned about group actions. In fact, these cosets are orbits of a certain group action. How do we do that? Set up H acts on G. Well, there are two ways of doing this. Let's start with the simpler one. H acts on G by just saying H dot G is H multiplied by G. Okay, and then the cosets are, the orbits for these actions are precisely, right? What is the definition of orbit? Hg, H dot G, H in H, which is just Hg. So right cosets are orbits of the action of x, H, by left multiplication on G. So this is one action. There's another action of H on G. H dot G is G H inverse. I'd mentioned this action when I defined a group acting on itself. There were two actions, the left multiplication action and the right multiplication action. This is the right multiplication action. Somehow, because we're writing H on the left here, we need to put an inverse there to make this work. And the orbits of this are what? Well, this is G times H inverse, where H is in H. But of course, H inverse is in H if and only if H itself is in H. So this is the same as GH. So the right cosets and the left cosets are orbits for the action of H on itself by left multiplication and right multiplication respectively. So our usual theory of group action says that G is a disjoint union of H orbits. So G is a disjoint union of left cosets or right cosets. H. And each of these cosets has the same size, namely the cardinality of H. So how many cosets are there? So let's use some notation here. So I'll write G mod H to denote the set of left cosets of H, and I'll sort of mirror this G mod H but written in the opposite, so H backslash G is what it becomes, but usually G mod H on the left, set of right cosets. So what we know is that G is a union of its left cosets, a disjoint union of its left cosets. G and each left coset has the same size as G itself, as H itself. So G is, the cardinality of G is the number of left cosets times the size of each left coset, which is the size of H itself.